It's time now to have an MNA tutorial. The problem at hand is to solve a circuit, to find the voltage in every node, to find the current in every branch, to find the power in every element. We begin with a very simple exercise, one that has only independent sources, only round sources. This one has 4 independent sources, 2 V sources, 2 I sources, and 5 resistors. All resistances are given in ohms, the V sources in volts, and the I sources in amps. Let's begin. Our first task is with nodes. Choose a reference, this one down here. Even a binary node would do, right? I've chosen a true node, the one on the bottom of the circuit. Then identify every node with a number, 1, 2, 3, 4, or with a voltage of the node V1, V2, V3. There you have. Those are the 3 nodes we will be writing KCL equations for. Remember, never write a KCL equation for the reference. You would only get a linear combination of the equations in 1, 2, and 3. Next step, choose the current direction in every branch, but not in I branches. In I branches, you already know what is the direction of the current, as here in the 5 amp source and in here in the 10 amp source. Those are given. The same if you have a controlling current or a controlling voltage, the directions already given for you have been chosen. First question we always ask when we solve a circuit in MNA, is there any controlling variable? In this case, no, there isn't. There is no controlled variable, no square rhomboid source, so no CTL equation, no CTL variable. Second question, always, is there any evil branch? If you don't know what is an evil branch, please watch the previous video on types of branches. This is a silly but memorable nickname we have given to V branches. Only one, that is an evil branch. We will need an evil current for that one, which is an unknown. We write the equation of the evil branch, which is voltage of the positive node. V2 in this case is voltage of the negative node. V reference 0 plus the value of the source 5. So in this case the equation is simply V2 is 5 volts. Sweet equation. That current, the current in the evil branch, we have nicknamed before, looking for a very silly name, an evil current, I sub E1. And that is an unknown. Now we write a KCL equation for every node, every true node, but not for the reference, for each node that we have identified. KCL for node number 1, the one here on the top left, is currents entering the node. There is only one at the very top. Always check how many currents are entering or leaving the node. That way you know in advance how many terms your KCL equation is going to have. On the left, the ones that arrive, on the right, the ones that leave the node. That way it's less likely that you may miss one of the currents. Currents entering, only 5 amps from the source here at the top. Currents leaving, 2. One through this R branch, V1 minus V2 over 2. And the other through this RV branch at the bottom, V1 minus V reference minus 4 divided by 2. But the V reference, we know it's 0. V1 minus 4 divided by 2, that is KCL for node number 1. For node number 2, we have 3 currents, left, right, and the one on the bottom. 2 entering, so we will have 2 terms on the left and 1 term leaving, 1 term on the right, the evil current one. The one on the left, we already know that. We could have copied and pasted the current from the previous equation, V1 minus V2 over 2. That is currents entering the node 2 from the left and from the right, V3 minus V2 over 3, another R branch current, and leaving an evil current, I1. KCL for node number 3, again we have 3 terms. 1 entry, 10 amps from the bottom, that is going to go on the left hand side of the equation, and 2 terms on the right hand side, entering 10 and leaving 5 amps on the top, and this current which is V3 minus V2 over 3, the current in an R branch. Now with the 4 equations we have, the evil equation that we had before, V2 is 5, and these 3 KCL equations we can solve for the 4 unknowns, V1, V2, V3, and the evil current. The values are 9.5 volts for V1, 5 volts for V2, V3 is 20 volts above the reference, and the current through the evil branch is 7.25 amp flowing from top to bottom. We look at that exercise and we cannot help but thinking there is an evil branch. That V branch we called an evil branch in our previous video because it makes us work more. It introduces one extra unknown, this one, I sub E1, and an extra equation, the one here on the top. More work, evil branch. However, can an evil branch like this one really be a good branch? An angel in disguise, is that possible? Let's see. Suppose that we don't really care for the current in that branch. We don't need to compute I sub E1. If that is so, we don't need to write the evil equation at all, right? No I sub E1, no evil equation, one equation less. But we realize also that the so-called evil branch is standing on top of the reference node and defining V2 without computation. V2 is 5 volts. 5 volts, you see? 5 volts and 5 volts down here. What else? We don't need to write a KCL equation for node 2 because V2 is known, right? That means one less equation. Two equations, two unknowns, V1 and V3. Solve them and look what you get. V1 is 9.5 volts, V3 is 20 volts. And of course, the formerly known as an evil branch is telling us that V2 is 5 volts. We have that data. If in the future we needed the current through this branch, in the middle, the 5 volts V source, well, we compute the 1-2 current, the 3-2 current, use KCL at node number 3, and with that we compute the current I sub E1. Simple, eh? So we realize that an evil branch can be a good thing, a good branch. And you may be thinking, okay, all of that is fine. From now on, I'm going to choose the reference on the negative side of evil branches. That way, I eliminate two equations, one evil equation and one KCL equation. Yes, that is a good idea. However, what if, for other reasons not in our control, the reference node is somewhere else, like this one? Can we take advantage of that goodness in the evil branch? Yes, we can. Check this out. I will call this unknown down here V1. It's node 1. And the one over here V2. That is node number 2. However, the voltage for this node on the positive side of the evil branch is not a new unknown. It is just the unknown V1 plus 5. Same unknown plus 5. We will consider the whole evil branch as a supernode. We surround it with the Gauss surface and write a KCL equation for that. This one, KCL equation for the supernode. How am I going to do that? Well, check this out. Check this out. Currents arriving in that supernode. Only one. The one on the top left from node V2 to V1 plus 5, right? That is the current in an R branch. Voltage of the origin V2 minus voltage of the destination V1 plus 5. That divided by the resistance 2 ohms. That is the current entering the supernode from the left. And currents leaving on the top. This would be voltage of the origin of the R branch V1 plus 5 minus V reference 0 divided by 3. Excellent. What else? Other currents leaving the supernode. The one here at the bottom, 10 amps on the right, and it is through an RV branch V1 minus V2 plus 4 divided by 2. That is the KCL equation for the supernode that comprises, that surrounds that so-called evil branch. And then we write a KCL equation for node 2 the usual way. We have two equations, two unknowns, we solve for them, and we have all the data that we need to compute every current, every voltage, and every power in that circuit. Think of an evil branch either as a supernode or as an angel branch. Your choice. But just write a supernode equation for that, and you will find a solution for the circuit with far less effort. Another exercise, one with controlled sources. Let's say that I do not really care for evil current, so I take advantage of that again with the evil branch on the left bottom side of the circuit. Reference node here at the bottom, why not? And then the voltage of this node on the top left is known, 8 volts. We have only two nodes that we need to write KCL equations for, node 1 here in the middle and node 2 on the right. Branch currents, the ones you see there. The others are defined by the current sources or by the controlling current IB. First question, is there any control current? Yes, there are two, one for VB and one for IB. VB is this voltage. You say that voltage is just V1 minus V reference. That is V1, right? And the second one, IB. Who is IB? IB is the current in an R branch. V1 minus V reference divided by 2.5. Two CTL equations. Any evil branch, we have already accounted for evil branches when we gave the value of the voltage to this node over here. We don't need to write an evil equation because we are not computing right away the evil current. KCL for node number 1, currents entering the node, only one from the top left, V2 minus V1 over 5, currents leaving, IB at the bottom, and this one, which is an RV branch, V1 minus 8 plus the value of the source, 1.0 times IB, all of that divided by 1 ohms. That is KCL for node number 1. Slow down or freeze the video and check the equations. Now for node number 2, one current arriving, 2 amps, and two currents leaving, arriving 2 and leaving, V2 minus V1 over 5, and the one on the top, that is a current source, 0.2 times VB. We have 4 equations and 4 unknowns, V1, V2, IB, and VB. Faster than a bullet, I mean faster than MNA. Sometimes we can solve a circuit just using carefully the basic principles of circuit analysis that we have seen in this series of videos before we even learned about MNA, current dividers, voltage dividers, simplifications, and applying KVL, KCL, or Ohm's law, or the 3 of them, or only 2 of them. And also keeping in mind that voltages are electric heights. This is true of smaller circuits very often. However, when everything else fails, we always have our safety net, our plan B, MNA. MNA still gets us home. Let's see how this works. But if you don't remember some of the words that I've mentioned in this slide, just go to the next page, to this one, and click on one of those links, or just review all the videos in this series. Let's begin with a very simple circuit. Case 1. We have 3 resistors, 1 voltage source, and the question is, what is the voltage VPQ? I have another question, but this one is for you. What is that current there? What is that current there? You say that is the current into an open circuit. That current has to be 0 amps. That's correct. But if the current is pointing that way, the voltage in the 5 ohm resistor, this one, is what? You say, oh, it's Ohm's law. R times I, 5 ohms times 0 amps, that is 0 volts. What does it mean? What that means is that this node 1 is exactly at the same electric height than node P. So we need to find what is the height of node 1, and that will be VPQ directly. How do we find that? Because as this current here between 1 and P is 0, then all of this area in this cloud is a voltage divider with no load. We have 10 volts being divided between these two 5 ohm resistors. Of course, V1 is going to be just half of 10 volts, 5 volts. That is V1. But the question remains, who is PQ? We've learned that node 1 and node P are at the same height. That means that V1 is just V PQ, 5 volts, and that is the answer to this question. Let's say for a moment that you are in an exam and you have a mental block. You freeze. In that case, we go back to the basics. We use MNA, reference node, here, right? And then identify the nodes 1 and 2. And you're thinking, hey, wait a minute, why are you calling node P1? Because I want the voltage of node P, so I explicitly name it a node. And then what? Branch currents, I choose them like so. Questions. There is no CTL equation, of course, and no evil equation, just two KCLs. Let's write them. KCL for node 2, for this one current going in, 10 minus V2 over 5, 2 currents leaving, V2 over 5, and this one, V2 minus V1 over 5. And KCL 1, only 2 currents, one going in, V2 minus V1 over 5, and leaving, we have the current into an open circuit that we know is 0. 0 amps are leaving that node. Two equations, to a node, we enter them into the simulator. I gave you the link to download for free, and we solve for V1 and V2, and we get V1 is 5, but V1 happens to be a VPQ, 5 volts, which is exactly what we got before, but this time using MNA. You may be thinking that is overkill, right? It is like killing an ant with a proverbial cannon, but it's an exam and you froze. In that case, whatever gives you the solution, MNA always gives you the answer. Another exercise, another simpler circuit, case 2. I've replaced the resistor on the top right with a V source of 4 volts. We again are asked to find what is VPQ, the voltage between P and Q, how much higher P is than Q. I ask you what is the current there. Again, it is the current into an open circuit. It is 0 amps. But if that current is 0 amps, then what we have in this blue cloud is a voltage divider with no load. We are dividing 10 between 3 and 2. How many volts we have here? V1. 10 multiplied by 2 divided by 3 plus 2. That is 4 volts. 4 volts here. Let's review what we're seeing here, right? Node 1 is higher than node Q here at the bottom by V1 by 4 volts. But node 1 also is higher than node P by 4 volts. That means that P and Q are at the same height. That is, VPQ is 0 volts. What if in the exam you freeze, you forget many things and details? In that case, just use MNA, reference node, right? Here, identify nodes 1 and 2 in this case, select the branch currents, and write your equations. Well, you say any CTL, no, but there is one evil branch now between nodes 1 and 2 and an evil current. It is one that we need to solve for. We need 3 equations. One evil equation, V2 is V1 plus 4, and 2 KCL equations. So this one for node 1, currents going in, the evil current I sub B, currents leaving, 0 amps. And then the KCL for node number 2, that is 10 minus V2 over 3 going in and leaving V2 over 2, and the evil current. 3 equations, 3 unknowns. We solve it and we get that V1, this voltage here, which is VPQ, is 0, same as before, but with MNA. A third case, another simple circuit. In this case, I've replaced the V source by this pair, resistor and the current source. The question remains, what is VPQ? Well, we say the current leaving on the right is 0, And then the current entering that Gauss surface from the left is 0 amps. That current is 0, which means that all this circuit is a voltage divider with no load. The voltage here is, of course, a divider of 10 between 3 ohms and 3 ohms, 5 volts. The voltage of this node here in the center is 5 volts. But let's apply KCL to this Gauss surface here on the far right. Currents going in, 2 amps from the bottom, leaving on the right 0 amps into the open circuit, and the current into the 2 ohm resistor on the top. Use KCL, and you tell me, what is the current at the top? 2 amps go in, 0. This have to be 2 amps as well. Those 2 amps produce a voltage drop in that 2 ohm resistor with that polarity, and the value, Ohm's law. V is Ri, 2 times 2, 4 volts. That means that node X is higher than Q by 5 volts, but node P is higher than X by 4 volts. That means that P is higher than Q by how many? 9 volts. And there is your answer. VPQ is 9 volts. Now let's do that using MNA. Just MNA. Reference node, nodes 1 and 2. Any CTL equation, no. Any evil branch, no evil branch. Only 2 KCL equations for node 1 and node 2. Let's write them. Here, for node 2, currents going in again, 10 minus V2 divided by 3, leaving V2 over 3, plus 2 amps, plus V2 minus V1 over 2. And KCL for node 1, it is 2 currents going in, 2 amps, and V2 minus V1 over 2, and leaving 0 amps. 2 equations, 2 unknowns entered that in the simulator and solve, and you get that V1 is 9 volts, which is VPQ, same as before. The point here is that you can solve this circuit faster with a thorough understanding of circuit analysis. But if you freeze, you can always recur to MNA to find a solution. Let's say now that we have computed all the node voltages one way or another, and we want to compute the branch current. Remember, to solve the circuit is find the voltage in every node, find the current in every branch, and the power in every element. Let's compute some branch currents. Here's the circuit, and voltages are given. 0 for the reference node, 5 volts in the middle, 9.5 and 20 volts. We obtain them. With those, let's compute the branch currents. At the top, that's easy. It's just the value of the current source, 5 amps. On the bottom right, the value of the current source, 10 amps. And now what? And now the current here in this R branch is 9.5 minus 5 divided by 2. 9.5 minus 5, that is 4.5 divided by 2, 2.25 amps. The current on this branch is 20 minus 5, that is 15, divided by 3, 5 amps. The current here is the current in an RV branch. 9.5 minus 0 minus 4, that is 5.5, divided by 2, that is 2.75 amps, flowing like so. We have now to compute the current in the middle. In this 5 volt source, we use KCL here in the 5 volts node, and we say 2.25 plus 5, that is 7.25, flowing downwards through that 5 volt source. Currents down. Now we move on and find what are the voltages in every element in the circuit, beginning with this one. How do I know that the voltage in the 4 ohm resistor is 20 volts with that polarity? The polarity is given by the current in the branch, imposed by the current source, 5 amps, flowing from right to left. So the right node has to be higher than the left node. That is why. Water falls from the sky. And the value, Ohm's law. Ri, 4 ohms times 5 amps, that is 20 volts. Next one. What is the voltage here? 15. How do I find that? It's how much higher the right 20 is than the left 5. 20 minus 5, that is 15 volts with that polarity. And here, the voltage is again given by Ohm's law. The current is 10 amps given by the current source on the bottom right hand side, multiplied by 3 ohms, 30 volts with that polarity because the current is flowing through that resistor from left to right. And in here, 5.5 volts because the current is flowing from left to right as well, and the value is 2 ohms times 2.75 amps, that is 5.5 volts. The voltage in this 2 ohm resistor is just 9.5 minus 5, 4.5 volts. What is missing? The voltages in the current sources. Remember, those voltages are such that we don't know until we solve for them. And for that, I'm going to use KVL. Let's begin with this question mark voltage on the 10 amp source. For that, I will use a KVL equation in this loop where I know every other voltage, but not the question mark in the current source. Let's begin here where I wrote start, flowing clockwise from start, going up by 30 volts, plus 30, going up by 5, plus 5, going up by 15, plus 15, going down by question mark, negative question mark. I arrived at the starting point again, and that is my KVL equation. Plus 30, plus 5, plus 15, minus question mark, that's 0. Solve for the question mark. That voltage in that 10 amps current source is 50 volts. Is that the only way to compute that? Of course not. We could have used this other loop. More computations, but why not? Let's start at the same point here and proceed again clockwise. From start to the left, going up by 30 volts, going up by 5.5, going up by 4, going down by 4.5, and going up by 15, and finally going down by question mark, that is 0. Check it out. Going up by 30, up by 5.5, up by 4, down by 4.5, up by 15, and down by the question mark. Arrive at the start point equals 0 and solve for the question mark, which is again, of course, 50 volts. Is that it? No, we could have chosen this shortcut. Between the reference node and the node at 20 volts, the voltage is going up by 20, so we can write a very simple KVL equation there. Beginning here, going up by 30, plus 30, going up by 20, and going down by question mark. The question mark voltage in the current source is 50 volts. Okay, let's find now what is the voltage in the other current source. The one here on the top, the 5 amps current source. Let's use this loop. KVL equation starting here. Well, starting here, that would be going up by 20, going down by 15, going up by 4.5, and going down by question mark equals 0. Solve for that. The voltage there is 9.5 volts. Now that we have voltages and currents in every element, we can compute what is the power in each one of them. I'll leave that up to you, but I will include the values here. Let's compute that for only a few. The convention for power is we will write as positive the power if the element is absorbing the power. And if the element is delivering power, we write that power as negative power. That is the convention of the distribution engineer that we will use in this course. The power here is absorbed 100 watts in element A. Multiply 20 volts times 5 amps, that is 100 watts. Because the current is flowing from high to low, the element is absorbing power. That's why I'm writing that as a positive number. And in here, the power in this current source, the 5 amps current source, is voltage 9.5 times current 5 amps, that is 47.5 watts in element D. But because the current is flowing from low to high, that source is delivering power, and I represent the power as the negative value, negative 45.7 watts. And I compute all the other values. I leave that up to you to compute all of them and check their correctness, both in magnitude and in sign. And that is the end of this short tutorial on MNA. Thank you very much, and I hope to see you all again in our next video.